In this lecture, I am going to solve a problem on a variable twisting moment. Okay. Find the diameter of a shaft to transmit twisting moments varying from 5000 Newton meter and 2000 Newton meter. The ultimate tensile strength is 600 Newton per mm square. Yield stress is 450 Newton per mm square. Assume stress concentration factor as 1.2, surface finish factor as 0.8, size factor as 0.85, and factor of safety as 2. Okay. So here in the problem, the shaft is subjected to a varying twisting moment that varies between 500 Newton meter to 2000 Newton meter. Okay. So in the torque problems, we don't need to take the minimum load in the negative direction. So if the minimum load is given in negative in the problem, then we can take it, or otherwise you can directly take the minimum load value. So T minimum is equal to 500 into 10 power 3 Newton mm, because in the problem it is given in Newton meter. So I am converting it into Newton mm. It is 500 into 10 power 3 Newton mm. Then the T max is 2000 into 10 power 3 Newton mm. The ultimate tensile strength is 600 Newton per mm square. Then the yield strength is 450 Newton per mm square. The stress concentration factor is directly given. It is 1.2. It is Kf is equal to 1.2. Surface finish factor and size correction factor, it is 0.8 and 0.85. Finally, the factor of safety is given. It is 2. So this is the Soderberg equation for twisting moment. In the place of sigma, you will have tau here. So 1 by n is equal to tau m divided by tau y plus kf tau a divided by ksr, ksz and tau minus 1. So here, since it is shear load, ks also will be there. Okay. And here the tau m is tau max plus tau minimum divided by 2, and tau a is tau max minus tau minimum divided by 2. So in the problem, the factor of safety n is given. We have to calculate tau m, tau a we have to calculate, tau y is not given. So actually in the problem sigma y is given, so tau y we have to calculate, kf is given, then the remaining terms are given, the correction factors are given. Finally, the endurance limit we have to calculate. So first we'll start from tau m and tau a. Tau max is equal to, we know that the maximum shear stress equation is 16T divided by pi d cube for circular cross section. In the case of maximum stress, it is 16T max divided by pi d cube. Okay. So the T max is 2000 into 10 power 3 divided by pi d cube. So if you substitute this, finally you will get 10,185.9 into 10 power 3 divided by d square. Then in the case of minimum stress, substitute 16 T minimum divided by pi d cube, you will get 2546.48 into 10 power 3 divided by d square. So now you can substitute this tau max and tau minimum in the mean stress and variable stress equation. So these kind of problems we have already solved. So you will get tau mean as 6366 into 10 power 3 divided by d square, and tau as 3820 into 10 power 3 divided by d square. So we have calculated tau m and tau a. Then the tau endurance. We know that if the endurance limit stress is not directly given, then we can select the equation from page number 1.42. And in the 1.42 you can see that for torsion, the tau minus 1 is equal to 0.22 times of your sigma u. So I am going to use the equation tau minus 1 is equal to 0.22 sigma u. It is 600. Then finally we will get tau minus 1 is equal to 132 Newton per mm square. Then the tau y. So actually in the previous problems we will use the sigma y problem, sigma y values, since it is normal stress. But here we have to substitute the value of tau y. And from the page number 7.6, as per the maximum shear theory, tau y is equal to half of the sigma y, that is sigma y divided by 2. So if the sigma y is given in the problem, then we can calculate the tau y value from the sigma y value. So tau y is equal to sigma y divided by 2. It is 600 divided by 2, that is equal to 300 Newton per mm square. Now we'll substitute everything in the Soderberg equation. It is 1 by n. Tau m is 6366 into 10 power 3 divided by d square. So this is mean stress we have already calculated. Tau y we have calculated, it is 300. Factor of safety is 2. Then kf, it is directly given in the problem, it is 1.2. So we can substitute that. Then tau a we have calculated, substitute the value. Then ks, we know that ka is 0.8, kb is 1. Similarly ks is the load correction factor for shear, it is 0.8. Remember that ks is equal to 0.8. So substitute the value of ks, ksr and ksz is given in the problem. Then tau minus 1 we have calculated, it is 132. Substitute everything. By solving this equation, finally you will get d is equal to 55.41 mm. Okay. So this is how you have to solve the variable twisting moment problems. So it is same like your variable normal stress. Only thing in the equations, instead of sigma m and sigma a, you will have tau m and tau y, and tau y should be calculated by using the maximum shear equation, that is tau y is equal to sigma y divided by 2. The tutorial problem: a shaft having an ultimate tensile strength of 630 megapascal, sigma u is 630 megapascal, and yield strength is 510 megapascal, sigma y is 510 megapascal, is subjected to a torque which varies between 2000 Newton to minus 800 Newton. So the T minimum is minus 800 into 10 power 3 Newton mm. It is given in Newton meter, so I have converted it into Newton mm. Then T maximum is equal to 2000 into 10 power 3 Newton mm. Using Soderberg method, calculate the diameter of the shaft. Take Fy is equal to 2. So the factor of safety value n is given as 2. Assume suitable values for other relevant data. So actually in the problem they have given sigma u, sigma y, tau minimum, tau max and n. But the stress concentration value is not given. Also we don't have any drawings to find the stress concentration value. So we have to assume the stress concentration value. So let us assume a stress concentration value of Kf is equal to 1. So assume that there is no stress concentration. So assume Kf is equal to 1. Similarly for Ks, it is, since it is shear load, Ks is equal to 0.8. Okay. So it is almost like the previous problem. Only thing we have to assume the value for stress concentration factor. Okay. So substitute everything in the Soderberg equation, then you will get diameter is equal to 53.42 mm.